The fundamental currency of our universe is energy. It lights our homes, grows our food, and powers our computers. We can get it lots of ways too, burning fossil fuels, splitting atoms, or solar panels. But there's a downside to everything. Fossil fuels are extremely toxic. Nuclear waste is, well, it's nuclear waste, and we don't have enough batteries to store sunlight for cloudy days yet. And yet, the sun seems to have a virtually limitless amount of energy. The sun shines because of nuclear fusion. In a nutshell, fusion is a thermonuclear process, meaning that the ingredients have to be incredibly hot. So hot that the atoms are stripped of their electrons, making a plasma, where nuclei and electrons bounce around freely. Since nuclei are all positively charged, they repel each other. In order to overcome this repulsion, the particles have to be going very, very fast. Now, in this context, that means they are extremely hot, millions of degrees hot. However, in a star, they cheat. They reach these temperatures because they're so massive. The pressure in their cores generates enough heat to squeeze the nuclei together until they merge and fuse, creating a heavier nuclei. And in the process, they release energy. It's that energy that the scientists are hoping to harness in their new generation of power plants, a fusion reactor. However, on Earth, it's not feasible for us to use this brute force method to find or create fusion. So we wanted to build a reactor that generates energy. From fusion, we have to get kind of clever. To date, scientists have invented two ways of making plasmas hot enough to fuse. The first type of reactor uses a magnetic field to squeeze plasma into a donut-shaped chamber, where the reactions take place. These magnetic confinement reactors, such as the ITER reactor in France, use superconducting electromagnets cooled with liquid helium to within a few degrees of absolute zero, meaning that those reactors host some of the biggest temperature gradients in the known universe. The second type is called an inertial confinement reactor. It uses a pulse from a superpowered laser to heat the surface of a pellet of fuel, imploding it, briefly making the fuel hot and dense enough to fuse. In fact, one of the most powerful lasers in the world is used for fusion experiments at the National Ignition Facility in the US. These experiments and others like around the world are just experiments. Scientists are still developing technology and coming up with new and brilliant ideas for fusion. Right now, it costs more energy to run the experiment than it does with the energy that they actually produce with the fusion reactor. The technology has a long way to go before it's viable, let alone commercially viable. And in some people's theory, it may never be possible. But if it gets there, according to Princeton University, it will be so efficient that seawater could be used to produce enough energy to meet future demands for millions of years to come. And this is because fusion reactions would use hydrogen or helium as fuel, and seawater is absolutely loaded with hydrogen. But not just any hydrogen will do. Specific isotopes with extra neutrons called deuterium and tritium are needed to make the right reaction. Deuterium is stable, can be found in abundance in seawater, and is readily available. Though, tritium is a bit trickier. It's radioactive, and scientists from the Science Direct journal say there may only be roughly 20 kilograms of it in the world, roughly 44 pounds. Mostly, it's obtained and kept in nuclear warheads, which makes it even more so expensive. So we kind of need to come up with a different idea or a different isotope that we can use. Scientists have found that helium-3, an isotope of helium, might also be a great substitute. Unfortunately, it's incredibly rare on Earth. However, the moon has supposedly got the answer for us. Scientists from the Remote Sensing Journal suggest that over billions of years in the past, solar wind may have built up massive deposits on the moon. Instead of making helium-3, we can mine it. If we could sift the lunar dirt for helium, we would have enough fuel to power the entire world for thousands of years. another argument for establishing a moon base if you weren't already convinced. Now, while it might sound crazy to still build a mini sun and put it on Earth, they are a lot safer than most other types of power plants, as explained by the International Atomic Energy Agency. A fusion reactor is not like a nuclear reactor where it can melt down catastrophically, end up having radiation for many, many years to come. If the confinement failed on a fusion reactor, the plasma would expand and cool, and the reaction would simply stop. Put simply, it's not a bomb. The release of radioactive fuel like tritium could pose a threat to the environment. Tritium could bond with oxygen, making radioactive water, which would be dangerous, especially if it seeps into the environment. Fortunately, there's no more than a few grams in use at a given time, so a leak would be quickly diluted and we'd move on. So there's nearly unlimited energy to be had at no expense to the environment in something as simple as water. So there would be a catch, right? Of course there is. It's cost. We simply don't know if fusion will ever be commercially viable, and even if they work, they might be too expensive to ever build. And the main drawback is that it's unproven technology, and it's a gamble. And that money might be better spent on other clean energy that's already proven itself. Maybe we should cut our losses, or maybe when the payoff is unlimited clean energy for everyone, it might be worth the risk.